In this virtual lecture, we will discuss a brief introduction to first-order systems. What we'll do is introduce two main concepts. We'll talk a lot about terminology, so you'll hear some of the terms that we use in describing first-order dynamical systems, and we'll discuss a very useful visualization tool that we can use to study first-order systems. This tool is powerful because we don't have to do a lot of mathematics to use it, but it gives us a good sense or qualitative understanding for how the system, a first-order system, behaves. So let's begin with some introductions. A first-order system consists of only one dependent variable. For example, that variable might be the voltage. There's also an independent variable in the system. Typically, it's the time, and we're interested in understanding how our dependent variable, the voltage, evolves as a function of our independent variable, the time. So as an example, a concrete example of a first-order dynamical system, let's remember our leaky, integrate, and fire model. So here's our leaky, integrate, and fire model. We have these conditional statements, and then we have this expression, which we derive from the RC circuit. When the voltage is small enough, we evolve the voltage according to this first-order differential equation, or dynamical system. So let's focus on this first-order dynamical system. It has one dependent variable, the voltage, and we're interested in understanding how this voltage evolves as a function of time, where time is the independent variable. This evolution depends on the voltage itself, our target voltage, and a time constant. So, in this example for our RC circuit, which is a first-order dynamical system, we can think of it as a one-dimensional, or sometimes it's also called a one-dimensional dynamical system. And the reason for that is that we can plot this this system on a single axis. So we can plot the result on only one axis, the voltage. So for example, we can imagine the voltage evolving in this one-dimensional axis. And typically, to represent this evolution, we plot the voltage as a function of time. And we might examine how the voltage, this one-dimensional variable, evolves as a function of time. Now I know this looks like a two-dimensional plot, and we'll think about this more carefully. In particular, how the voltage evolves only on this single axis. And again, we'll get to that in the next few slides. So this first-order dynamical system, we'll sometimes loosely call it a first-order differential equation. So this differential equation defines our first-order dynamical system. When we're looking for a differential equation, we're looking for something like d by dt. So in this case, we have d voltage dt. This defines our differential equation, which describes how our dynamical system evolves in time. Now, in this course, we'll use the term dynamical system and differential equation somewhat interchangeably. But differential equation, we're always looking for how something evolves or how something changes, in this case, as a function of time. Okay. Now, these first-order dynamical systems or differential equations come in two general classes. There are first-order autonomous differential equations. These have the form du dt, where u is our dependent variable and t is our independent variable. We want to know how u, our dependent variable, evolves in time. It's going to equal to some function f, which depends only on u. This is an autonomous differential equation. Notice we only have our function f depending on u, and typically these systems are easier to handle and will be our focus in this course. Another general class of first-order systems consists of non-autonomous differential equations, non-autonomous. What that means is we have our variable u, it's changing in time, so we have du dt, and now our function f depends both on u as well as the time t. So note here there's an explicit time dependence, this explicit dependence on our independent variable. Now in this case, u is a general variable. It could represent the voltage or the concentration, some ion, or maybe a gating variable or an activity. That's the power of mathematics. We can describe many different things, many different physical objects using a similar set of equations. So a very important comment, what we'll focus on here, again, is autonomous systems, where we will not have this t on the right-hand side of the differential equation. Instead, we'll just have our dynamics depending on the variable itself, not on time. It turns out that our analysis of autonomous systems can be applied to non-autonomous systems if the time-dependent parameters are pulses or constant in time. So let's consider a particular example where we inject an input current, I input, that changes in time. And we'll choose a particular time dependence for this injected current. So here's our I input. We'll set it at some baseline level initially. We'll then turn it up and set it to a constant level for some interval of time, and then we'll return it to our baseline level. So here we're showing I input, our input drive, which is changing as a function of time. And now we have an explicit time dependence on the right-hand side of our differential equation. The trick to analyze this non-autonomous system is to try to break it up into separate intervals where this input is constant. So we might try to analyze the system in this first interval where the input is constant, and then analyze it in the second interval and this third interval, and then try to paste them together. So that's one trick we could try to use if we have a non-autonomous system where the stuff in our function f is changing in time, and it doesn't depend on u. Right? It's changing explicitly as a function of time. We might try to break it up into intervals where this time dependence no longer exists, and then paste those together. We might run into these types of examples, but typically we're going to again focus on autonomous systems where the right-hand side of our differential equation, this variable f, only depends on the dependent variables, not on time. Okay, so some mathematical notation. We'll introduce three terms here that we'll use throughout the rest of the lecture. Phase space. This consists of all possible values of our dependent variable u. Now in this case, for our one-dimensional phase space consists of a line. So we can draw this one-dimensional phase space. Here are all the possible values for our variable u. We can imagine this line goes off to negative infinity and positive infinity. So our system lives here. Our one-dimensional system lives here on this line. One note, this idea of phase is confusing, especially confusing in neuroscience. Phase can have lots of different interpretations in neuroscience. Here, phase space will refer to this particular object, the entire space in which our dynamics can live. Another definition, trajectory. This is the motion of a point through phase space. So how do our dynamics evolve on this phase space? And we can think of this as a parametric plot. And we'll show an example of this in a second. And the trick is we're not plotting here the variable u versus time, or dependent versus independent variable. So let's think about this parametric plot. And we can try to imagine this as a movie. We'll show snapshots of this movie here. You'll have to use your imagination to think about what this movie would look like. So here's our phase space. We know that our dynamics live in this one-dimensional space, somewhere on this line. We can ask, where is the system at time t equals 0? It's at a particular value. We ask, what is u at time 0? And here it is. It corresponds to this red dot at time 0. As time evolves, we can then ask another question. We go into the future at time t equals 1. Where is the variable u? Well, here it is. It's at another point on this line. This is a u evaluated at time 1, and so on. We can ask, where is the variable u at time 2? Here it is at some other point on the line. So we could think of our trajectory, in this case, as a bead. This red dot we can think of as a bead that can move along this one-dimensional line in time. And we could slide this bead to the right or to the left. And how that slide occurs is determined by our function f for our differential equation. And again, we'll get into this as we look at more examples. So we have a trajectory, this bead moving along the one-dimensional line in time. The last term we'll think about is a fixed point, which corresponds to a constant value of our variable u. So we'll set this we'll define this u of t is equal to u sub fp. Fp for fixed point. Notice we've eliminated the time dependence here because we've said u is a constant value. It no longer depends on time. So if u is a constant value, what is du dt? Well, if it's a constant, u is not changing in time. Right? A constant value means u is not changing in time. So du dt at a fixed point must be 0. So du dt, our differential equation, is equal to 0 at the fixed point. Another way to say this, we have our du dt, we evaluate it at the fixed point, which means we're going to evaluate our function f, which defines our dynamical system at the fixed point u. Again, we have in this case our autonomous system. F depends only on u. We evaluate it at the fixed point. We know that at the fixed point, u is constant. It's not changing in time, so we set it equal to 0. These are sometimes also called stationary points. Again, stationary because u is not changing. We could think of our marble as, or our bead as fixed or stationary on this line, or equilibrium. And typically I'll try to use the term fixed point, but I might slip into these other terminologies every once in a while. Okay, so how do we solve a first-order differential equation? The traditional way, and the way you learned about probably in your calculus class, is given some initial condition. So the value of our variable u at time t equals 0, we want to find the function u over all time. So we want to know, how does our variable evolve over time? That's a solution to our system. This is often very difficult and sometimes impossible to do. What we're going to focus on in this class is a geometric way of solving first-order differential equations. And the idea here is that we can use pictures instead of formulas to describe the important aspects of the behavior of a system. We might miss some of the details, but we're going to focus on the most salient features of this system. And ideally, we can get a lot of important information about the behavior of the dynamics with not too much effort. And again, that'll be our focus here. What's nice about these geometric approaches, it consists of pictures. We can solve some algebraic equations and get a lot of insight for how the dynamics evolve. So how do we actually perform a geometric analysis of a first-order system? Well, it consists of 3 steps, which we'll outline here in the abstract, and then we'll apply to a specific example. So the first step, step 1, is to draw the phase space. And to make this a little bit more concrete, let's consider this somewhat abstract system. We have our variable u changing in time, our first-order differential equation du dt. It depends on some function f of u, which we haven't specified yet, but we will. Okay, so step 1, in our analysis of this first-order system, we need to draw the phase space. We'll see what that consists of for all of our first-order systems. This first step is often very easy. I'll do that one for you in most cases, and you'll have to think about the more complicated parts in steps 2 and 3. Okay, so step 2, after we draw the phase space in step 1, we're going to draw dots to represent the fixed points. And remember, fixed points correspond to the values of f that are equal to 0. So we want to know, where is du dt equal to 0, or where is f evaluated at u fp equal to 0. So f evaluated at the fixed point, it's equal to 0. U is not changing in time, it's fixed. So step 2, draw dots to represent the fixed points. And then in the last step, we'll draw arrows to indicate the flow between the fixed points. And what does this mean, the flow between the fixed points? Well, we're going to ask a particular question. Is u, our variable, moving away or towards each fixed point? And if we can answer that question, then we'll be able to draw the flow. We can phrase this in a more mathematical way. We can ask, is our function f greater than 0 or less than 0? Remember, if f is greater than 0, f of u is greater than 0. If f of u is greater than 0, looking at the top right of our slide, that means du dt is positive. If du dt is positive, that means u is increasing in time. While if f of u is less than 0, that means du dt is negative. If du dt is negative, then u is decreasing in time. So let's consider an example of this geometric analysis and applying our 3-step procedure. To do so, we'll consider an example where here in this case we'll set du dt, our differential equation for our dynamical system. We'll set it equal to u squared minus 1, where this function u squared minus 1 corresponds to our function f as a function of u. It's an autonomous system. Notice there's no explicit time dependence here. And we've made this function f explicit in this case, because we want to be able to work out an example. So we've chosen a particular form for f in this case, u squared minus 1. Now I know I said there were 3 steps, but often we'll find that there's another 4th step that's useful, and I'm going to call it here step 0. And what we'll do in this step is we'll plot f, our function in the right-hand side of our differential equation, versus our variable u. And that function is shown here, this plot is shown here at the right, where we're plotting on the vertical axis f versus the dependent variable u. Now, maybe it comes as no surprise that this function, what we're plotting here is u squared minus 1. It's a quadratic that points up. Right, it points up. If we go off to a positive infinity or negative infinity, we expect this function to increase. So we have this quadratic function as drawn here. The line f equals 0 corresponds to the x-axis in this case, the horizontal axis. So this horizontal line is where f is equal to 0. And that'll be useful later on. So this is step 0. We've plotted our function f versus the variable u. And we'll see why this is useful as we go along. Okay, so now step 1. We'd like to draw the phase space. Now I'll do this part for you. How do we draw the phase space? It's a one-dimensional dynamical system. We know that our dynamics must live on this line. So the dynamics live on this one-dimensional line. They can move back and forth on this line, but we can always specify the state of the system at some point on this line. So there it is. We've drawn the one-dimensional phase space. It's just a line. I've drawn it here horizontally. You might imagine that this line goes sideways or up and down. It's more useful, at least for me, to draw it horizontally. Okay, step 2. Let's indicate the fixed points. And now, remember the fixed points are where our function f is equal to 0. So we want to know, where does our function f here at the top of the screen, where does u squared minus 1 equal 0? Now we can solve this equation. We can ask what values of u do we need to choose for this function u squared minus 1 to be 0. But we can also see it directly from our figure on the right. Now, where are the fixed points? They correspond to the values, or the values of u where our function f is 0. And we can see by visual inspection of this figure that there are two fixed points. There's one here on the left where our function f crosses the horizontal axis. This corresponds to a value of u equals minus 1. We can check this. If we plug in minus 1 to our function f, we get minus 1 squared is 1. So we have 1 minus 1 is 0. Good. There's another fixed point. Again, we can see it directly from our picture. Actually, before doing that, let's plot this point in our phase space. So we're going to take this point, u of minus 1, and we're going to indicate this fixed point in our phase space. So here's one fixed point. There's another fixed point. Again, we can see it directly from our figure, our plot of f versus u. The fixed point corresponds to the crossing of our function f and this horizontal axis. That's where f is 0. And we find here it's a value of u equals 1. Again, we can plug this in. Let's check it. If u equals 1, then if we look at our differential equation, u squared, 1 squared is 1, minus 1 is 0. Good, we're at a fixed point where du dt is equal to 0, no longer changing. And again, let's indicate this fixed point in our phase space. So now we've drawn our two fixed points in the phase space. Our last step in the geometric analysis of this system is to indicate the flow. And we're going to do this by considering two intervals in our system. So let's first consider the interval of u between the fixed points. So by that I mean this interval, the interval between the two red circles, between the fixed points. Now if we want to understand the flow, we need to understand what is the value of f, or what is the sign of f in this interval. And if we look at our figure above, we can see that between the two fixed points, f is negative, right? This function dips below the horizontal axis. Now, if this function is negative, what does that mean for du dt? Well, that means du dt is negative. And if du dt is negative, how does u change? Well, u decreases in time. Du dt is negative, u is decreasing in time. And we can indicate that graphically in our figure with an arrow. And that's shown here. So we're going to use this arrow to indicate that between the two fixed points, the value of u gets smaller. It decreases in time, so it's moving to the left. So that's between the two fixed points. What about elsewhere, outside of this interval? Well, if we look outside of this interval, for example, let's look to the left of the leftmost fixed point, so over here in the top of the figure, we can ask, what is the sign of f in this interval? Well, looking at our plot, we see that in this interval, f is positive. Right? I can see it here. F is positive. And if f is positive, du dt is also positive. So if du dt is positive, that means u must increase. So u increases in time. And we can indicate that graphically in our figure. So here we have u increasing in time. It's moving to the right. U is increasing. What about over here, to the right of all of our fixed points? Well, again, we see in this interval, f is positive. If f is positive, then du dt is positive. Right? F is positive, du dt is positive, and if du dt is positive, then u must increase in time. And again, we can indicate that graphically in our figure by drawing an arrow. So we indicate the flow. So the power of this approach is it takes minimal work to get a qualitative description of the dynamics. And to illustrate this, let's consider choosing a starting value of u and deducing what happens. So for example, what if we choose a value of u between the two fixed points? So looking at our arrows in the system, if I start at the cursor here, what happens to u? Well, it decreases until it gets to this fixed point. And notice at this fixed point, we know that we're fixed, u is no longer changing in time. So that tells us if we start anywhere between these two fixed points, u decreases until it hits one of the fixed points. What if we started somewhere on the left? Well, here our differential equation tells us that u increases. We can look at the flow, right? The arrow's pointing to the right, so u increases until we hit this leftmost fixed point, u equals minus 1. What if we started way over here at the right? Well, in this case, the arrow is telling us to move to the right. So if we start to the right of all of our fixed points, u increases, and it continues to increase indefinitely. So it goes off to infinity. So no matter where you start, you could choose a u anywhere in this interval, and we can say where that value of u will end up in the long run. We may not understand all of the details dynamics of the system, but we know what will happen if we let time run long enough. U either converges to this fixed point on the left, or it blows up and goes off to infinity. So now let's return to our leaky, integrate, and fire model. We already saw that the LIF model does not make an action potential on its own. Remember when we were studying this system, we had to tack on this hack. We added a threshold and reset in order to create something that we called spikes whenever the dynamics hit the threshold value. Now, another question we can ask is, can any first-order system make an action potential? We've chosen one first-order system, the leaky integrate and fire, which we constructed using an RC circuit. But maybe there's some other first-order system where we can ignore this hack, this threshold and reset, and still produce action potentials. So let's consider this. The question we would like to answer is there some function f as a function of v, such that dv dt is equal to this f, and we'd like to have the following solution. So we'd like our solution to look like this. We'd like v of t to increase in time rapidly, decrease rapidly, have this after hyperpolarization, and then return to rest. So we want to know, can we choose some f of v where v can evolve in this way? And to answer this question, let's look at the trajectory of this action potential in the phase space of this one-dimensional dynamical system. So what is the phase space for this one-dimensional system? Well, the phase space is simply a line. And we could draw that line here. Our one-dimensional system consists of the voltage V that's evolving along this one-dimensional line. And what we'll do is let's try to take this trajectory that we've drawn at the top of the picture, V if it was a function of time evolving in time, and let's plot it on this one-dimensional line. Okay, let's start at some time t equals 0. That corresponds to some voltage, and let's set that voltage, let's choose that voltage to be here on our line, so over near the left. I've drawn this circle slightly above the line. You'll see why that's important. Remember that we can think of the dynamics as a bead that's evolving along this line. It can never move off of the line because our dynamics live in this one-dimensional space. But for convenience, I've drawn this circle slightly above the line. And again, you'll see why that's useful as we go along. Okay, so this is time t equals 0. We're at some resting voltage. We know that at time t equals 1, the voltage rapidly increases. So how does that look on this line in our one-dimensional phase space? Well, we know that this bead will rapidly swing over to the right and reach some new value at time t equals 1. So we have a higher voltage value of V as the cell rapidly depolarizes during the upswing of a spike. Then what happens? We know at time t equals 2, let's call that 2 here, the voltage rapidly decreases, and that's shown here. We see V of t rapidly decreases, and how does that look in our one-dimensional phase space? Well, we have our bead resting on the line over here at the peak of the voltage. It then rapidly decreases and moves to some value slightly less than our rest value. So we now have our bead resting over here to the left of our figure at time t equals 2. We then allow time to evolve for a longer interval, maybe out to time t equals 10 in this case. And the value of the voltage, this bead will slowly move over to the right and eventually return to our resting position. So here we can imagine what's happening in this case. Our bead is starting at t equals 0 on the left. It's rapidly increasing to a depolarized value, a larger V at the right, and then rapidly decreasing. It overshoots our resting value at time t equals 2, and then it slowly increases and returns to rest at time t equals 10. And what I'd like to do is focus on one interval of this phase space, indicated by this black box. And let's consider the flow of the dynamics inside of this interval. Now, in order for this system to occur, to reproduce an action potential with this rapid increase and decrease in the voltage, it requires that the flow point to the right. We drew this here. From time t equals 0 to t equals 1, the dynamics move to the right. And we'll indicate this here with a rightward pointing arrow. And for that to be the case, our function f of v must be positive. We want v to increase rapidly. F of v must be greater than 0. Now also notice, within the same interval, we require the flow to point to the left. Right after time t equals 1, from time t equals 1 to t equals 2, the voltage rapidly decreases. So we know the flow here must also point to the left. Right? If we were to choose a voltage in here, it must also point to the left. So that means f of v in this interval must also be negative. So we need to find some function f such that if we choose a value of v within this black box, that function is both positive and negative. And I challenge you to find a function that's both positive and negative for some value of v chosen in this interval. Right? And it turns out this cannot be. You can't find a function f that for some fixed value of v is both positive and negative. And so what this suggests, and again, stating that here, our function, we can never find a function that can be both positive and negative of a fixed v. And another way to say this is that we require our function f of v to be unique at each value of v. It only has one value. If you specify a value of v, then you get a unique value of f of v. It can't have two different values. Okay? So what do we conclude from this? So what this suggests is that first-order dynamical systems, which consist of only one variable, cannot make an action potential spike. So we're not able to make an action potential using only a single variable. So given a system of this form, dv dt is some function f of v, we have our first-order dynamical system, we cannot make this system produce an action potential with a rapid increase and decrease in voltage. We looked at this as a particular example of F. We developed our RC circuit as part of our leaky integrate and fire model, and we know that we had to add in this hack in order to produce a spike. And it turns out you can never find a first order system that can produce a spike. It's not possible. And the power of this is we didn't have to prove this result by checking every single possible form f of v. Right? Maybe if we had a different type of circuit, we could still produce a one-dimensional system. We might hypothesize that we could find a one-dimensional system that could produce an action potential, a spike. But that's not the case. The insight from the geometric picture is no matter how we choose f, we will not be able to develop a first-order system that produces a spike. And again, remember, our leaky integrate and fire system only spikes because we included our hack. We said that if the voltage is big enough, we'll declare that a spike and then reset the voltage. It doesn't spike on its own. How do we get a system to spike? How do we generate a voltage trace that looks like this? We have to add a bunch more variables, and we saw that in the Hodgkin-Huxley model. In order to produce an action potential or spike, which is biophysically meaningful, we had to introduce 3 additional gating variables, m, n, and h. And we'll return to that later in this lecture. As another example of this geometric approach to understanding a first-order dynamical system, let's consider a new model, in this case the quadratic integrate and fire model. To construct this model, we'll update our leaky integrate and fire model. And here's the quadratic integrate and fire model. Here's the definition. If V is less than some threshold value, V threshold, then we're going to evolve the voltage V using this differential equation. dV dt is equal to V itself squared plus some target voltage, V star, divided by tau. I've indicated here that V star may depend on time, but in this case, let's consider V star to be a constant. On the other hand, if V exceeds this threshold or is equal to the V threshold, then we're going to set it to the reset. Now, a question, what's different between the original leaky integrate and fire model and our new quadratic integrate and fire model? Well, there are 2 important differences. First, we have a V squared term. Originally, this term was linear, it was V, and now we include a V squared component. The second difference between the original LIF model and the quadratic integrate and fire model is the sign. All the terms in this model are positive. There were some minus signs floating around in our leaky integrate and fire model. Those are all gone. Good, so this is the new model we'll consider here with particular focus on this first order differential equation. First order because there's only a single d by dt. And we can see our single variable that's evolving in time, v. Okay, so let's perform a geometric analysis of this first order quadratic integrate and fire model. Start with step 1, we need to draw the phase space. This is always the easiest part. It's typically nice to start our analysis with a simple step to build some confidence. So what is the first step? We want to draw the phase space. It's a one-dimensional phase space. It's a line. So we have this line, our one-dimensional phase space. We'd like to understand how V, our voltage, evolves along this line. We can imagine it as a bead that slides along this line as a function of time. Good, so that's step 1. We've drawn the one-dimensional phase space, this line. Step 2, we'd like to indicate the fixed points on this line. How do we find a fixed point? Well, we want to know where dV dt is equal to 0. So we want to know where is the voltage no longer changing? Where is it fixed? To do that, we can solve our differential equation in this case. Let's do it analytically. So we'd like to solve this differential equation. We take our the f of v, the right-hand side of our differential equation for the quadratic integrate and fire model, and we now have written v squared, and we've indicated a subscript here, fp, for fixed point. So we want to know what is the voltage at the fixed point, squared, plus the target voltage divided by tau. We'd like that to equal 0, because that will specify dV dt equals 0. To solve this equation, we can only the numerator matters in this case. The denominator is always a positive constant, so we want the numerator of this equation to equal 0. How do we do that? Well, we can rearrange and solve for VFP. And what do we find? Well, we'll have to move this V star over to the other side of the equation. So we have a negative V star, and then we'll need to take the square root of both sides of the equation. And this is the solution that we find. Plus or minus the square root of minus v star. Not a very pretty equation, but correct. Why is it not pretty? Too many minus signs, in my opinion. But that's what we find. So we've indicated the fixed points in this case, and we find that there are two fixed points. We have plus the square root of minus v star and minus the square root of minus v star. It's a quadratic function, so we're expecting to find two fixed points when they exist. Okay, so that's the second step in our analysis. We've indicated the fixed points. Now in the third step, we'd like to indicate the flow on the phase space. And in order to indicate this flow, it's useful to plot our function f of v, which is the right-hand side of our differential equation, our quadratic integrate and fire model v squared plus v star over tau, where this v star we're going to assume is constant. Let's not worry about the time dependence. And we'd like to plot this f of v versus v. In order to do this, we're going to have to choose values for our time constant tau and v star. And let's, for convenience, set them both equal to 1. Or, we'll set the tau equal to 1 and v star equals minus 1. You might consider what happens if this were a positive 1. But in this case, let's set v star equals minus 1. And here's a plot. So what we're showing in this figure is our function f of v, this quadratic v squared plus v star over tau. That's plotted here in blue. And this horizontal line corresponds to our horizontal axis. This is our variable v, so we're plotting fv versus v. This horizontal axis also indicates the value f equals 0. So that's indicated by the horizontal axis. This is the value f equals 0. F is positive above this line, and f is negative below this line. Good. So where are the fixed points in this figure? Again, we solved for them numerically on the previous, or analytically on the previous slide. We can now solve for them graphically in this figure. Where are the fixed points? Well, they correspond to the intersections of our curve, f of v, and this horizontal line. So we want to know where is f of v equal to 0. Here's one point at minus 1, and another point at plus 1. Now remember, we had a formula for the fixed points, v of fp. We solved for this on the previous slide. We said it's equal to plus or minus the square root of minus v star. V star in this case, we've said is minus 1. So minus, we have this minus sign and then a minus 1. So we have the square root of 1. What is the square root of 1? Well, 1 times 1 is 1. So the square root of 1 is 1. And we have two solutions. We have a plus 1 and we have a minus 1. And these correspond to our two intersections of the blue curve, f of v, and this black line, which corresponds to the horizontal axis where f is 0. So two intersections, a quadratic function, one intersection at v equals minus 1, and the other intersection at v equals plus 1, which we can find through our formula we found on the previous slide. Good, so we've indicated our two fixed points, and now one thing you might notice is that this one-dimensional line we've drawn here, this black line, is our phase space. We've said our phase space is one-dimensional. It's the values of v as they evolve in time. And we've drawn this one-dimensional phase space here. We can think of this black line as our one-dimensional phase space. And we've indicated the two fixed points with circles. We have a fixed point at minus 1 and a fixed point at plus 1. Remember, at these fixed points, f of v is equal to 0. Okay, so let's now draw the flow on our phase space. To do that, let's consider what is the flow. Well, we'll consider it in three separate chunks of our phase space. Let's start all the way to the left for values of v less than our leftmost fixed point, so less than minus 1. V over here on the left. Well, what is f in this interval? Well, we see that f of v, if we look at our blue curve, it's always positive. It's always above this horizontal black line. So if f of v is always positive, that means dv dt is also always positive. And if dv dt is positive, that means v must be increasing. And we'll indicate this increase by drawing a red arrow pointing to the right, indicating that v is increasing in this yellow interval, moving to the right. Let's consider another interval, this second interval shown here in orange. Again, we'd like to ask, what is the value of, what is the sign of f of v in this interval between the two fixed points? If we look at the blue curve, we see it falls below the horizontal axis here. So in this case, f of v is negative in this orange interval. If f of v is negative, what is dv dt? Well, dv dt is equal to f of v, so it's also negative. And if dv dt is negative, that means v decreases in this interval. And we can indicate this decrease graphically by drawing a red arrow pointing to the left. So that tells us if we choose any value of v in this interval, it'll decrease and move to the left. Now finally, what about the last interval beyond all of our fixed points over to the right? So for values of v greater than +1, in this interval, the sign of f of v is positive. Again, we can see that by our blue curve. It's above the horizontal axis, so it's positive in this case. dv dt is equal to f of v, so it's also positive in this interval. And if v is positive in this interval, dv dt is positive in this interval, then v must be increasing in this interval. And again, we indicate this increase graphically by drawing a red arrow pointing to the right. So v is increasing, moving to the right in this last interval, all the way on the right. So in this way, we can use our plot of f of v versus v to draw to indicate the flow in our phase space. Notice our phase space now consists of two fixed points, these red circles, and then the flow within each of the three intervals. So now, given this geometric analysis of our quadratic integrate and fire model, let's examine how this model behaves. To do that, we'll return to our phase space. Remember, our phase space for this one-dimensional system is a line. It's all the possible values of v, which can go from -infinity to +infinity. We have two fixed points, which are indicated by circles in our quadratic function, and then we've indicated the flow to the left of all the fixed points, between the two fixed points, and then to the right of all the fixed points. And now let's examine the case where we choose a value of v that starts on the left of all the fixed points. So let's imagine we choose a value of v that starts here on the left of the figure. We can imagine we place a bead on this line, and then what happens? Well, if we look at our arrow, it tells us we move to the right, and we continue moving to the right until dv dt is equal to 0, until we get stuck at this fixed point. So what happens in this case? We start our value of v on the left, and it moves until it goes to a fixed point. It reaches this resting value, the leftmost fixed point. What if instead we chose a value of v that started between our two fixed points? So we place our bead on the line, we then look at the flow. The flow is telling us move left. So we take our bead and we move it to the left until it reaches this same fixed point. So again, if we choose a value of v between the two fixed points, we move over to the left and we go to this fixed point, or rest. And now let's consider the interesting case. What if we start here, all the way to the right of our fixed points? What happens in this case? Well, our arrow tells us to move to the right. So our arrow tells us if we start to the right of all of our fixed points, we want v to increase. So we take our bead, we start it right here, and we move it to the right, and the value of v increases. Now this increase can happen indefinitely. So v could increase off to infinity. But what we're going to impose in this model, remember in our quadratic integrate and fire model, is a threshold. So we take our bead and we move it to the threshold. Eventually we hit this threshold value shown here as a purple line. When we hit the threshold, we then take our bead, we disconnect it from the line, and then we reattach it over at v reset. Just like we did in the leaky integrate and fire model. So we take our bead and then we ask what happens, how does the voltage evolve in this interval, to the left of all of our fixed points after we're placed the bead at v reset. What happens in this case? Well, we look at our arrow and we see that the flow is moving to the right, v is increasing, so we take our bead and we slide it to the right until we hit the leftmost fixed point. And this is the power of the geometric analysis, No matter what value of v we choose on this line. So you can specify any value of v. And if you specify that value, we can look at this figure and tell you eventually what will happen. So if we choose v over on the left, we see it goes to a fixed point. If we choose it between the two fixed points, it also goes to that same fixed point. If we choose it to the right, we hit threshold. We spike in this toy model, We spike when we hit threshold. We then go to the reset, and we eventually go to rest. We haven't solved any differential equations, but we have a very deep understanding for how this system behaves. We might miss some of the details, but we can always tell how does this system behave as time goes off to infinity. And in this case, no matter where we start, we always end up at this resting value. We might spike once or we might not spike at all, but we always end up at this resting value. And again, I hope this illustrates the power of this geometric approach. By drawing some pictures, maybe doing some algebra, we're able to get a deep understanding for this differential equation. Okay, now the last part of this lecture, let's consider whether or not we can apply this powerful geometric analysis to a more complicated model, our Hodgkin-Huxley model. Now remember, our Hodgkin-Huxley model consisted not of one variable, but of 4 variables evolving in time. So instead of a first-order differential equation, we now have a fourth-order differential equation. We have 4 dependent variables, our voltage V and our 3 gating variables, N, M, and H. All of them are evolving in time. Here's our system of differential equations for the Hodgkin-Huxley model. We have dv dt, so we have one differential equation, dn dt another one, dm dt another one, dh dt another one. So we have 4 differential equations, 4 variables that are evolving in time. And if we wanted to visualize the phase space for this system, it's no longer in one-dimensional space. Our phase space is now 4-dimensional. So the Hodgkin-Huxley dynamics evolve in a 4-dimensional phase space. And we can try to represent that graphically. So we might start with one dimension. So here's one dimension, it's a line. Maybe that corresponds to the variable v. Let's then add in another dimension. So we'll choose the variable n, and now we have a plane, right? We have our vertical axis and our horizontal axis. We have this plane that's 2 variables. We might add in our third variable, m. We can think of this as a line that's sticking out of your screen, so we now have a 3-dimensional space, right? But we need one more dimension. So we have this 3-dimensional space, and I'm not sure how to draw this other dimension. We have to somehow add in another axis. These dynamics evolve in a 4-dimensional space. So you can think of this system, this 4-dimensional system, as a point that lives in this 4-dimensional space. And this point is somehow moving in this 4-dimensional space in some way that's impossible for me to visualize. What's happening in this 4-dimensional space? One difficulty of the Hodgkin-Huxley model is it's hard to look at. Right? We have 4 variables we need to examine, and we can't simply plot them on a line or a plane or a 3-dimensional space. It's evolving in 4 dimensions. Okay, so given that, can we perform a geometric analysis of our Hodgkin-Huxley model? Well, let's consider the 3 steps in this geometric approach. The first step is to draw the phase space. And we've already seen that this is complicated. How do we draw a 4-dimensional phase space? I don't know, but I've drawn some cartoon representation of it here. And well, even if that's a problem, let's keep going, right? Maybe we can figure out some way to do that. Let's think about step 2. Can we find the fixed points for the system? And then step 3, how do we indicate the flow in this 4-dimensional system? Well, let's focus on step 2. We already know that drawing the phase space is complicated. Maybe we can somehow find the fixed points. How do we do that? Right? Can we find the fixed points in our Hodgkin-Huxley model? Well, maybe we can. We have our 4 differential equations. If we want to find the fixed points for this system, we want to set each differential equation equal to 0. So we want to set dv dt equals 0, dn dt equals 0, dm dt equals 0, dh dt equals 0, and then solve. So we want to solve for v, n, m, and h. So we have 0 is equal to all this stuff in the first equation, 0 is equal to all this stuff in the second equation, where remember n infinity and tau n are really complicated functions of v. 0 is equal to all this stuff for m, and 0 is equal to all this stuff for h. And it turns out you can try to do this, but there's no analytic solution. So we can't find the fixed points analytically. And we know that visualizing the system is also very hard. So we might wonder what to do, right? We need some other way to analyze this system. So to summarize, geometric approaches are very powerful ways to understand low-dimensional dynamical systems like the leaky integrating fire, the quadratic integrating fire, and they become less useful for higher-dimensional systems like Hodgkin-Huxley. We'll apply these approaches throughout the rest of this class in particular examples, and we'll also think of other ways we can try to make sense of more complicated systems when these geometric approaches are not so useful.